So next part of the discussion in covalent bond is covalent bond formation in hetero-atomic molecules. Covalent bond formation in hetero-atomic molecules. The best examples of covalent bond formation in hetero-atomic molecules is CH4 methane, NH3, ammonia, which contains one lone pair on the nitrogen, and H2O, which contains two lone pairs on the oxygen. CH4 is methane. CH4 is methane molecule, hetero-atomic. It is hetero-atomic because you are finding that it has different atoms in it. It has carbon and hydrogen atom. So it is methane molecule, hetero-atomic. Go for ammonia. Again it is NH3, different atoms, water, H2O, water, polar covalent molecule. Again it is hetero-atomic. So if you take methane, if you use the Lewis electron dot structure method, Lewis electron dot structure method for covalent bond formation. So if you take methane, here take carbon as a central atom and 4 hydrogens, you align them in the 4 corners like this. Each hydrogen has 1 valence electron and each carbon has 4 valence electrons, 1, 2, 3 and 4. So each hydrogen will try to share 1 electron of carbon, resulting in the formation of 1 bond pair. Same thing applies for the second hydrogen. It will share its 1 electron with the valence electron of carbon, third hydrogen, fourth hydrogen. We are finding that here each hydrogen is able to acquire duplet stability. Each hydrogen in this methane, each hydrogen has duplet stability and each oxygen has octet stability. So that means here if you carefully analyze this structure of the methane molecule, each bond pair will result in the formation of 1 covalent bond. There are 4 hydrogens aligned at the 4 corners of the tetrahedron with respect to carbon, which is central atom. 4 bond pairs are there, so therefore the final structure goes like this: first carbon hydrogen bond with 1 covalent bond, second carbon hydrogen bond with second covalent bond, third carbon hydrogen bond with the third hydrogen, and fourth carbon hydrogen bond with fourth hydrogen. You are finding that there are 4 covalent bonds which are formed in the methane molecule, and this methane molecule, therefore it results in the tetrahedral symmetry. It is a tetrahedral molecule. Shape is tetrahedral, it's a tetrahedral molecule. Similarly, if you go for, that is after methane, if you go for ammonia, that is you go for ammonia, this is methane, you go for ammonia. If you go for ammonia is the central atom. Apply the Lewis electron dot structure method. If you apply the Lewis electron dot structure method, that is each hydrogen has 1 valence electron. So that 1 valence electron I am highlighting here. Each nitrogen has 5 valence electrons. That 5 valence electrons also I am highlighting here. That is I am using crosses 1, 2, 3, 4 and 5. So what you are noticing here is 3 hydrogens will try to share their valence electrons with the 3 valence electrons of nitrogen, and they result in the formation of 3 bond pairs, and 1 lone pair, 1 pair of electron out of 5 valence electrons, 2 electrons out of 5 valence electrons of nitrogen, 2 valence electrons are not involved in the bond formation. So these pair of electrons will result in the formation of non-bonding pair of electrons. Those are called lone pair. electrons. So therefore finally if you take the structure of ammonia, this ammonia structure looks almost like this. We have 3 nitrogen hydrogen bonds and 1 lone pair here, 1 lone pair. So this ammonia molecule right now it has 3 covalent bonds between nitrogen and hydrogen. 3 covalent bonds are there and 1 lone pair of electron is there. So if you take the structure of this ammonia molecule, you find that this is the structure and its shape of the molecule is pyramidal. So it has 3 nitrogen hydrogen bonds in the form of covalent bonds and 1 lone pair of electron on the central atom, that is nitrogen. Similarly, if you go for the third molecule, that is water molecule, here I have bit of space, so I am going to finish up the third molecule also. If you take water, H2O, it has 2 lone pairs over oxygen. So you take oxygen and hydrogen and hydrogen. Each hydrogen has 1 valence electron. So the 2 hydrogens I am showing with their respective valence electrons, and each oxygen is having 6 valence electrons. So 1, 2, 3, 4, 5 and 6. So each hydrogen will try to share with 1 electron of the oxygen. The first hydrogen will share its valence electron with the valence electron of oxygen. Second hydrogen will share its valence electron with the valence electron of oxygen, and you find that here 2 bond pair of electrons are there between oxygen and hydrogen. Out of 6 valence electrons, oxygen is trying to share only 2 valence electrons with respect to 2 valence electrons of hydrogen. Therefore it is giving 2 bond pairs and also 2 non-bonding pair of electron, that is 2 non-bonding pair of electrons. So therefore here each hydrogen in the water molecule is trying to acquire the duplet stability, but whereas the oxygen is trying to acquire octet stability, because if you count the total number of electrons surrounding the oxygen in water molecule, 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is trying to acquire octet stability. That's why if you take the further structure of water molecule, it almost looks like a V-shaped molecule resulting in the formation of oxygen hydrogen bond and oxygen hydrogen bond, and another pair of electron of oxygen. 2 pairs of electrons of oxygen are not involved in the bond formation. So the molecule more or less it becomes angular, and they are acquiring duplet as well as octet stability. So here one thing what we have to understand here is, if you take methane, ammonia and water molecule, in methane the central atom carbon is undergoing octet stability and the adjacent atoms, that is hydrogens, are acquiring duplet stability. Similarly, if you go for ammonia molecule, the central atom nitrogen is trying to acquire the octet stability, but the adjacent atoms hydrogens are trying to acquire the duplet stability. If you go for water molecules, the central atom oxygen is trying to acquire the octet stability, which contains 2 bond pair electrons and 2 lone pair electrons. So 2 bond pair plus 2 lone pair of electrons results in total number of electrons which is equal to 8, and that results in octet stability. And rest of the 2 hydrogens in water molecule, because they have only 1 bond between oxygen and hydrogen, both the hydrogens in water molecule they acquire the